All right, y'all, welcome to this video where I will go over the entire study guide, including the warm-up, even though we went over it in class, because the goal is for you to understand every single part of this so that you can do well on your exam tomorrow. But of course, fast forward, pause, rewind, jump ahead, wherever you need. All right, let's dive in. Warm-up 1, let g be the polynomial function represented by g of x equals x to the fifth minus 25x cubed. A, determine the end behavior of g as x decreases without bound. Express your answer using the mathematical notation of a limit. Okay, well, end behavior is determined by the degree of the polynomial. This is in standard form, so the highest exponent is the degree, and that is, of course, x to the fifth. The fifth is an odd number, so the end behavior is going to be linear. So it's either going to be like this or like this. But this is a positive leading coefficient, so it's going to look like a positive linear function, which means I'm just left with this guy. So what happens? As x, which moves side to side, so it goes forever in this direction, what is happening to the output of the function? Well, we're clearly headed down, right? We're headed down. So we can say the limit as x approaches negative infinity. So as x goes forever in this direction, what happens to the g of x? Well, the g of x is going down towards negative infinity as well. Okay. Determine if the function is even, odd, or neither. Well, we said the end behavior is odd, but that does not guarantee that the function is odd. For a function to be odd, every single term has to be odd. Notice here I have two terms. I have x to the fifth and negative 25x cubed. Well, both of those terms are odd, so the entire function is odd. So I can say odd because all terms are odd. All terms have to be odd, right? If I added a x squared here plus x squared, this would no longer be an odd function. It would be neither, right? All of them have to be odd for it to be odd. All of them have to be even for it to be even. All right, part B, find all the zeros of the function and indicate their multiplicities. Well, this was given to us in standard form, but for us to find the zeros, we need to be in factored form. So I'm going to need to factor this. We can see that each term here has an x to the third inside of it. So I can pull out an x to the third and rewrite this as x third times x squared minus 25, right? I divided out x to the third from each term. But this can still be factored. This can be factored to x to the third times x minus 5 times x plus 5. And let's think about that. Why is that? Well, x squared minus 25 is really x squared plus 0x. There's no x terms there, minus 25. What two numbers add to 0 and multiply to negative 25? Well, that's, of course, negative 5 and positive 5. So we have now converted this to factored form. Once you're in factored form, to find the zeros of the function, you set each factor equal to 0. And we get x equals 0, x equals 5, and x equals negative 5. So those are our zeros. X equals 0, x equals 5, x equals negative 5. But notice it says to name the multiplicities. Well, because this is to the third power, that means that 0 really occurs 3 times. So this has a multiplicity of 3. These are both to the first power, so there's no multiplicities. All right, determine the intervals where the g of x is greater than 0. Well, to do that, we just need to sketch a graph of this function. We know we have zeros at negative 5, 0, and positive 5, and that our end behavior looks linear. So I'm going to start by coming up like this. I'm going to go through this negative 5 because this is really a multiplicity of 1. You don't need to write that. You don't need to write multiplicity of 1. That's implied. But when it's an odd multiplicity, we go through. So I'm going to go through this. Then I'm going to hit the 0. Again, it's an odd multiplicity of 3, so I'm going to cut through that again. Again, another multiplicity of 1 I go through. And it makes sense. Look, my end behavior is just like this little linear graph that I sketched. Now, there's some funky stuff happening in between because it's not really linear, it's to the third. But the end behavior looks like a positive linear function. So the question says, when are we greater than 0? Well, we're greater than 0 from here to here and from here onward. So we can say we're greater from 0 over the interval -5 to 0. Notice I use parentheses and not brackets because there's no equal sign here. Brackets are from when we're equal to something, or like greater than or equal to. And parentheses are when we don't want to include that point. We don't want to include -5 or 0 here. And we're also from, what is that, 5 to infinity. All right, so part C, sketch a graph of the function g. We already did that, and label all the relative max and min. Well, this is easy. This is a low point, so that's a minimum. This is a high point, so that's a maximum. All right, first FRQ in the books. Let's keep it moving to warm-up number 2. We have a table of some data here, and it says let f be a polynomial function. Selected values of f are shown on the table above, where k is a constant, okay? Find the average rate of change of g over the interval -3 to 3. Show the work that leads to your answer. Well, average rate of change is really that's just like finding the slope as if it was linear, right? So imagine I had something, just like picture this for a second. I had a graph that looks like this. Maybe it's kind of similar to our last graph. And it says, what's the average rate of change from here to here? Well, it's just saying, if this was linear, what would be the slope of that line? And that's kind of what we're asking ourselves here. So, slope, as we learned in Algebra 1, is the change in y over the change in x. So over this interval, what is the change in x? We'll do x first. Well, we change from -3 to 3. That means we are going up 6, so positive 6. And in y, we start at positive 24, and we go down all the way to -24. So we went down 48, and -48 divided by 6 is -8. So the average rate of change is -8 over that interval. All right. Find the value of k such that the average rate of change of f through the interval 0 to 2 is 5. So this time we have to work backwards. We can't teach you every possible question they can ask you in math. You have to be able to critically think. Well, we already know that m is equal to the change in y over the change in x. And we can see the change in x here. That's from 0 to 2. That's 2. But we don't know the change here because we don't know what k is. So this is really, k minus 0 is equal to 5. Right? This equals 5. It tells us that. Now we can just solve this equation right here. We're just solving this equation, right? Multiply each side by 2. These cancel. We get k minus 0 equals 10. Well, we don't really need a minus 0, right? What number minus 0 makes 10? 10. So if k is 10, there's an average rate of change of 5. All right. If f is odd, what is the value of k? Describe your reasoning. Well, let's peek at this table. I think, again, I don't think I taught even and odd functions that well. So let me just sketch something real quick. An even function, all right, even, it's going to reflect perfectly over the y-axis. So it might look something like this. Right? That's an even function. It looks the same on both sides of this. Right? It could look something like, I don't know, this. Right? That's an even function. Odd functions reflect over the origin right here. Right? So like a linear function, that goes through the origin, that's an odd function. Right? It looks the same in the diagonal sections. It looks the same. Okay? So these look the same. All right, so let's say, all right, it's odd. Well, what if we just plotted these functions on a graph? What if we just plotted these points right here on a graph? So let's just make a mini graph. I'll zoom in on it for a second. We have the points -3, 24. And again, I'm just kind of rough sketching it. -3, 24. And -2, 6. -2, 6, 0, 0. Right, that was on there. 2k, we don't know that. And -3, or sorry, +3, 24. +3, -24. Well, this, you can see that this is reflecting, right? Because I have a 3 at -24, and I have a negative, they're opposites, right? Even, if this was even, this blue dot would be right here. They'd be the same. They're opposites for odd functions. And we can see that here, right? This is -3, +24. This is +3, -24. Same thing here. If this is a -2 and a +6, this too must result in a -6. So the value of k is -6. It says describe your reasoning. Well, because when x is -2, g of x equals +6. We want the opposite to happen for odd, and that's easy to remember because opposite, odd, they both start with O's. Could the function be even? Describe your reasoning. Well, no, it can't be even, because if it was even, then this -2 resulting in a +6, or no, that's not the example I want. This -3 resulting in a +24, even would be the same. This would also be a +24, but it's not a +24, it's a -24. So it must be odd. No, because -3 and 3 have different outputs. They'd have to have the same outputs for an even function, but they don't. They have opposite outputs. All right, could the function be linear? Justify your answer using the table. Well, a linear function always has a constant rate of change. So here, let's say we have a change in y over the change in x is 1. We went down how many? We went down 18. So the change in y over the change in x here, from here to here, is -18. So for this to be linear, then this change needs to also be -18. They all need to be -18. So here we go down, or no, we go up 2. Here we go down 6. -6 divided by 2 is -3. So that's a vastly different than -18. This is not a constant rate of change. So no, the table does not show a constant, I'm just going to abbreviate, rate of change. All right, so we've finished both the warm-ups. It is time for a mind map, and I think some of you will be tempted to skip this part of the video, but I would argue maybe it's the most important part. The first unit is about polynomial and rational functions. We already took the assessment on polynomial functions. This one will focus a little bit more on rational, but it will have both. And you need to know both and maintain the knowledge all year. All right, so a polynomial function. Some people will say this is a function with many terms. I don't think that's that good of a definition because, we could have the f of x equals x squared. Some people say that's not a polynomial, that's a monomial because there's only one term. Poly means many. Well, watch this, plus 0x, plus 0. Now there's 3 terms. I didn't really change the function, it's still the same function. So I like to define a polynomial as having a number as an exponent, right? But a constant is also a polynomial, like the f of x equals 5. That's a polynomial, in my opinion. Watch this, plus 0x. So you kind of just know it when you see it. I'll tell you what it doesn't have, is it doesn't have a fraction, right? This is not a polynomial because that's a rational function, which we'll talk about in a second. And this would not be a polynomial. It cannot have a variable as an exponent. So like 5 to the x, that's an exponential function, which we'll talk about in the next chapter, or the next unit. All right, so let's see. What have we covered about polynomial functions? Well, we show these really in two ways. We show these in standard form. And that might be something like the f of x equals x squared plus 5x plus 6. And we can show that in factored form, which again, what multiplies to c and adds to b? Well, that would be x plus 3, x plus 2. So these are the same functions, just shown in two different forms. We can gather different information. Factored form is good at showing us the zeros of a function, right? I can just set these equal to 0. And standard form is good at showing us the degree. And it's really important to be able to determine the degree in factored form or standard form, right? Because students will say, okay, here I have degree of 1, degree of 1. I need to add those up and the degree is 2. But here, when it's in standard form, I'm just looking for the highest exponent, which is 2. It's 2. You do not add these. It does certainly not equal 3, the degree. The degree is 2 here. So being able to determine the degree of a polynomial is very important. I'll just sketch one here for a second. In your head real quick, come up with the degree of this polynomial. 3, 2, 1. If you didn't know the degree was 5, you still don't understand the degree of a polynomial, and that is one of the most foundational things you need for this unit. Okay, so what do those degrees mean? Well, the degree determines the end behavior. Okay, the degree determines the end behavior of a polynomial function. So, if the degree is odd, the end behavior, I'm just going to write EB, is linear in appearance, right? The end behavior is linear. So if it's a positive leading coefficient, it's going to slope up. If it's a negative leading coefficient, it's going to slope down. If the degree is even, the end behavior is quadratic. So if we have a positive leading coefficient, it'll open up. If we have a negative leading coefficient, it'll open down. Okay? All right, let's keep talking a little bit. Speaking of open up and open down, it's very important that we understand concavity. This is, I don't know why I'm starting with concave down here. This is concave up. This is concave down. This means that this has an increasing rate of change. Concave up, increasing rate of change. Concave down, decreasing rate of change. Well, we can disaggregate this a little bit. So like from here to here, I have an increasing rate of change. It's a negative rate of change, and it's slowly becoming positive. But so in this blue interval, I can say, okay, but the function's going down. It's going down, but the rate of change is increasing. So I could say I'm decreasing. The function is decreasing at an increasing rate. Right? And from this red interval, well, we're going up. And the rate of change is increasing because it's concave up. So we could say we're increasing at an increasing rate. And we can do that same stuff over here, right? This is concave down. But from here to here, the function's going up, 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 up. And so I can say that we are increasing. The function is certainly increasing. It's going up. But, I don't need a but, at an increasing rate. All right, I wish I had purple right here. I'll use yellow. I'll probably regret it right away. But here, the function is going down, right? And it's at a decreasing rate. So we can say we're decreasing at a decreasing rate. All right, so that's the big stuff for polynomial functions. We talked about even and odd functions. I'm not going to mind map that now. This is the most important stuff for us to understand about polynomial functions. It's not everything, though. All right, Let's hop into rational functions. Rational functions we typically define as, well, the r of x is equal to the f of x over the g of x, where f and g are both polynomials. So it's a polynomial divided by a polynomial. And like the most simple version of this might be like 1 over x. Typically, we're going to have an x in the denominator here. We're going to have an x in the denominator of the... If we don't have an x in the denominator or some variable, then it's not a rational function. One thing I guess I'll note is that means we're going to have like wholes and asymptotes in our rational functions. I think you're aware of that now. Jumping back up here to polynomial functions, they're continuous. All right, I don't know if I spelled that right. I'm going to erase, well, I'll just leave it. I'm bad at spelling. They're continuous, all right? That means there's no holes or asymptote. It just exists permanently. There's nowhere it's going to be undefined, a polynomial function. Rational functions are going to have holes and asymptotes, things of that nature. Well, let's talk about that. Where are these rational functions undefined? Well, there's two ways it can be undefined. It can have a hole, and that's going to look something like this. It's just a hole in the graph. Or it could have a vertical asymptote. There's a lot of words that are hard to spell in this first unit. And that's going to look something like this, where we have like some vertical line that we never touch because it's undefined there, right? So it reaches like this, and it gets closer and closer and closer and closer to this line, but it will never touch it because x, or the function, is undefined at that spot. Well, what results in these? Our general rule is that a hole results when we get 0 over 0, and that a vertical asymptote results when we only get 0 in the denominator, so like x over 0. But there is a little bit of an exception to this rule right here, the 0 over 0. If the multiplicity is higher in the denominator, so like, or the numerator, so say I have like x plus 3 squared over x plus 3, I'm tempted to say this is a whole because at x equals negative 3, I would get 0 over 0. But if the multiplicity of the numerator is higher, so the multiplicity of the factor in the numerator is higher, well, then it's going to go over to here. It's going to become a vertical asymptote. So, and that's all about what happens as we get closer and closer. Well, let me show you a little bit why. Well, this can be written as x plus 3 times x plus 3, right? This is x plus 3. Well, these cancel out. What are we left with on the bottom? 0. We're left with something over 0. Well, that's a vertical asymptote. So be careful. Make sure you understand that exception for the holes. And so I guess I'll just leave this example, like x plus 3. This does result in a hole because this goes over here. We should make sure we keep that. If the multiplicity of the factor is higher in the numerator, that's going to be a vertical asymptote. But if it's higher in the denominator, this is going to be a hole. And now you can use the same logic we just used. I can expand this. Well, these cancel. There's nothing left up here. And, well, if this is negative 3, this is also going to be 0. So we get 0 over 0. All right. So that's a hole and a vertical asymptote. These are where the function is undefined, right? There is no x value. There's no output at that x value for the function. Now, we have other types of asymptotes that speak about the end behavior of a function. End behavior. So let's say I have a horizontal asymptote. All right, that's just going to be some horizontal line that as I go towards positive and negative infinity, I don't touch. So I'll just draw that out like this. Okay, so, And look, you can even see a vertical asymptote here. There's nothing stopping us from having both a horizontal and a vertical asymptote. But you can't have a whole and a vertical asymptote in the same place. They can be in the same function, but not at the same place. All right, so this is a horizontal asymptote. And the other place asymptote that can tell us about behavior is a slant asymptote. And those are going to, like, asymptotes that look like linear functions. So it's going to be something like da-da-da-da-da-da-da-da-da. And it's going to be, I'm never going to touch this. So it's going to be maybe something looking like this, where I'm going to get closer and closer to that line, but I'm never going to touch it. Okay, so that's a slant asymptote. Well, how do I get these? A horizontal asymptote, if the numerator, or if the denominator is larger, so if, not larger, higher degree. If the denominator has higher degree, I'll always get a horizontal asymptote at y equals 0. Every single time. So an example of that would be x over x squared. Right? I have a higher degree in the denominator. I'll always get a horizontal asymptote at y equals 0. Now, if same degree, I'm going to get a horizontal asymptote at y equals a over b, where a and b are the leading coefficients of the polynomial. So say I had something like 3x squared over 2x squared. These are the same degree. I would have a horizontal asymptote at 3 over 2, the leading coefficients. Now, I kind of want, and this influences the end behavior, because here, as x is going towards positive infinity, sorry, I just erased some of this. What is happening? Well, we're going towards the asymptote. So if, like, I could write this asymptote in linear, if I have a, oh no. All right. I lost the rules a little. You have them. I crashed out. If I have a horizontal asymptote at y equals 0, I can write that as a limit statement saying the limit as x approaches negative infinity, then the f of x is equal to 0. I'm approaching that horizontal asymptote. I'm never getting there. Horizontal asymptotes speak about end behavior. And that's going to be the same thing in the positive direction. As x is heading towards positive infinity, the f of x equals 0. So I'm approaching that horizontal asymptote line, but I'm never reaching it. All right, looks like my slant asymptote graph is gone. I'm just going to redraw it. Slant asymptote. I do not know why the iPad crashes out like that and erases stuff. All right. So I have a slant asymptote that I'm never reaching. Boom. Boom. I'm getting closer and closer into it forever, but never reaching it. When does this happen? When the degree of denominator is 1 higher than numerator. Because I'm getting a linear function, right? If I have x squared plus 1 over x minus 2. Well, this is a quadratic up here divided by a linear down here. A quadratic divided by a linear is a linear. So I end up with this slant asymptote. And the end behavior resembles the asymptote. So, well, if I divide this, I'm going to get a positive linear function if I divide this. And so the end behavior is going to model that. And, well, what's the end behavior of a positive linear function? Well, I could say, just like I did up in the last example, I could say the limit as x approaches negative infinity, the g of x equals negative infinity. And the limit as x approaches positive infinity, the g of x equals positive infinity. So a slant asymptote is going to have end behavior that models a linear function. Now be careful. It's not always going to be negative, negative, positive, positive. Think about what might change that before I tell you. Think. Watch this. That would completely change everything. All right? Now the end behavior would look like this because the slant asymptote would look like that. All right, so just be careful. All right, that is enough mind mapping. Let's jump and do some actual problems here in part one. Part one, state whether each rational function has a horizontal asymptote, a slant asymptote, or neither. If there is a horizontal asymptote, write the equation for it. All right, so let's zoom in on number one here. Well, let's just talk about the degree of each, because the degree is really what's going to determine this. The degree, this top one is in standard form, so I'm just going to look at the highest exponent. So the degree is 2. I'm not going to write it like that. That's going to be confusing. The degree of the bottom is also 2, right? Because this is to the first, this is to the first. So the degree is the same. When the degree is the same, if you remember the rule, we're looking at the leading coefficients. So we have a horizontal asymptote at y equals a over b. Well, the leading coefficient here is 1. The leading coefficient here is 1, so it gets 1 over 1. We have a horizontal asymptote at y equals 1. So I'm going to say horizontal asymptote. I'm just going to abbreviate. I'm going to give it here at y equals 1. All right, again, we're looking at the degree. The degree of the top is 1. You know, you can't see it, but it's there. I think everyone understands that in AP Pre-Calculus. The degree of the denominator is 2. So we're certainly going to have a horizontal asymptote here because the degree of the denominator is larger. And when it's larger, it's y equals 0. All right, this is, we have to be able to determine the degree of these polynomials. Well, here is to the second, here is to the first, here is to the first. So this is a degree of 4 on top, right? This is a degree of 4. And this is also to the 4th degree. So again, I have the same degree. When I have the same degree, I have a horizontal asymptote at y equals a over b. So the leading coefficient here is 4. Leading coefficient here is 2. So I get 4 over 2. We all know that's 2. So I have a horizontal asymptote at y equals 2. All right, let's head down here. Again, let's look at the degree of these polynomials. Well, what is this? The degree here is 2. The degree here, 1 here, 1 here. Oh, that's also 2. So it's going to be a horizontal asymptote at y equals a over b. What? Well, I have a 1 here. It's invisible. Over -4, we get -1/4. So we have a horizontal asymptote at -1/4. All right, k of x. Again, I'm trying to confuse you at this point. Well, think about this. I could expand this. This is neither really in standard form or factored form. It's kind of in some in-between state. This could be written as x squared plus 8 times x squared plus 8, right? Well, how many x squareds are there? There's 2x squareds. So what's the degree here? 4. What's the degree of the bottom? Also 4. So another horizontal asymptote because they are the exact same. Are there no slant asymptotes on this? Interesting. Okay. I guess not. All right, so we have 4. Well, what's here? This is a 1, so we have a horizontal asymptote. Y equals a over b. We get 1 over, well, this is -1. 1 divided by -1 is -1, so we have a horizontal asymptote. Y equals -1. Here, what type of function is this? This is a polynomial. Polynomial. That's our good friend polynomial. That means it's continuous. There's no horizontal asymptotes. There's no slant asymptotes. So this is neither. We don't have asymptotes in polynomial functions. All right, part 2. Determine all the information below for each rational function. All right, so this first one, let's dive right in right away. Well, the domain, I could have a hole or an asymptote and a vertical asymptote, and the domain does not exist there. The domain is anywhere that the denominator equals 0. So that's going to happen here at, I know x cannot be -5, because if it is, this is going to be 0. X cannot be +2, because if it is, this is going to be 0. And 0 times anything is 0. If we get 0 in the denominator, it's undefined. You cannot divide by 0. So we can change this into interval notation and say, well, we exist from negative infinity to negative 5. We exist from negative infinity to 2. And we exist from 2 to positive infinity. The only places we don't exist are negative 5 and positive 2. All right, let's do our zeros next. Our zeros are where we get 0 only in the numerator. So I'm going to zoom in on the numerator, but look, this also appears in the denominator, so it cannot be a 0. Same thing here. X plus 5 exists in the numerator, but it also exists in the denominator, so it cannot be a 0. So we actually have no zeros to this function, no x-intercepts, none. All right, wholes. Now, wholes, we said 0 over 0, but there's an exception to that rule, when the multiplicity is higher in the numerator. So let's look at x plus 5. We have this here and here, but the degree is higher of this factor is higher in the numerator. So that's actually going to result in a vertical asymptote. And we might as well just fill that in while we're doing it. There's a vertical asymptote at x equals negative 5. Now, here, the degree is higher in the the denominator, right? So this will be a hole here at x equals 2. And again, these should line up. The domain does not exist anywhere that there's a hole or a vertical asymptote. So you can notice this here and here and here and here. That's exactly what we want. All right, slant asymptote. Well, a slant asymptote exists when the numerator has one higher degree than the denominator. So let's look at these degrees. Well, the degree up here, we have a 4 and a 3, so the degree is 7. Here we have a 3 and a 4, so the degree is also 7. So the degree is the same. There cannot be a slant asymptote. So there's no slant asymptote. You can't have both of these. You can't have both a slant and a horizontal. Got to choose one. So the degree is the same, so we know we're going to have a horizontal asymptote at y equals a over b. And our leading coefficients here are just 1 and 1. So we have 1 at y equals 1. End behavior. Well, we have a horizontal asymptote. And when you have a horizontal asymptote, that's where your end behavior is headed. So we can say the limit as x approaches negative infinity. What's this function called? F. F of x is equal to 1. And the limit as x approaches positive infinity, f of x is equal to 1. All right. Jumping over here. We are in standard, both of these polynomials, look right here, are in standard form. Let's factor them. And we're going to factor out an x to the third. Or not an x to the third. Factor out an x. And we get x squared plus 5x plus 6. Of course, that can be factored even more. So we get x times x plus 3 times x plus 2 all over, what's this factor to? X plus 3 and x plus 1. All right, hopefully you can read that. So the domain, we cannot be negative 3, because it's positive 3 right here, and we cannot be negative 1, because that positive 1 right there. So we can write this in interval notation that we exist from negative infinity to negative 3, from negative 3 to negative 1, and negative 1 to positive infinity. The zeros are places we exist in the numerator, but not the denominator. Well, this x plus 3, that exists in both, so it's not going to be that. This x is by itself in the numerator, and this x plus 2 is by itself in the numerator. So we're going to have a 0 at x equals 0, and at x equals negative 2, because remember, I'm setting those factors equal to 0. All right, I'll switch colors. Let's do wholes. Wholes are where I exist. I get 0 over 0. Multiplicity is either the same or larger in the denominator. Well, I have an x plus 3 multiplicity of 1, x plus 3 multiplicity of 1. So I must have a hole at x equals negative 3. Vertical asymptote when I get only 0 in the denominator. x plus 1. Well, so that means the vertical asymptote at x equals -1. Notice again, alignment with the domain and the holes in the asymptotes. All right, slant asymptote happens when the degree of the numerator is 1 higher than the denominator, and that's exactly what we have here. Degree of up here, the degree is clearly 3, the degree is clearly 2. So we can do some polynomial long division. X to the third plus 5x squared plus 6x divided by, I'm just going to write this smaller off to the side, x equals -1, divided by x squared plus 4x plus 3. All right, I'm asking myself, what do I need to multiply x squared by to get x cubed? Well, that is x. So I can write my x up here. X squared times x is x to the third. 4x times x is positive 4x squared. 3 times x is 3x. And just like with regular long division, I'm going to subtract. These cancel. 5x squared minus positive 4x squared is 1x squared. And 6x minus 3x is 3x. Okay, now it is x squared times what makes 1x squared? Well, that's clearly positive 1. Oh, I got a constant. As soon as I got a constant, I'm done. That's my slant asymptote. So it looks like y equals x plus 1. There's going to be a slant asymptote. That means there is no horizontal asymptote, and it's time to talk about end behavior, which is going to resemble this slant asymptote. A slant asymptote or a horizontal asymptote is going to tell us our end behavior. Well, x plus 1, that's a positive sloping linear function. So I can say the limit as x approaches positive infinity, what is this, g of x equals positive infinity. We're going up. I switched the order here a little. It should be negative infinity first. No one's going to knock you for that, but doesn't really make sense. All right, and I guess I'll just show this in Desmos real quick, where we can say, okay, we have the g of x is equal to, let's put this in parentheses, x to the third plus, no, we didn't want to close that parenthesis, plus, what is it, 5x squared plus 6x, close the parentheses, divided by, what is it, x squared plus 4x plus 3, x squared plus 4x plus 3. And if I put a slant asymptote at x plus 1, look, that is the asymptote there. This is getting closer and closer and closer and closer and closer to it. And look, there's always a distance. It's getting closer to it, but it never hits it. That's what a slant asymptote is. All right. If you can do these and understand them, then you're doing well. All right. Now let's get a little more difficult. Part 3, writing an equation for a graph. Clearly, I'm giving you rational functions here. All right. What do we notice in this graph? I notice 2 things right away. We have a horizontal asymptote at y equals 1. So I'm just going to make a note of that. Horizontal asymptote at y equals 1. And we have a vertical asymptote at what? X equals 2. I don't see any holes or anything like that. So that's what we're working with. Well, to get a horizontal asymptote at y equals 1, we must have the same degree. They have to be the same degree, and the leading coefficients have to be, 1 over 1 or 5 over 5, something like that. Has to divide and equal 1. To get a vertical asymptote at x equals 2, then we need to have the denominator cannot equal 2. So I'm thinking about this one first. I'm going to want to have something like this in the bottom, x minus 2, right? Because if I set that equals to 0, I'm going to... All right, so then I can literally come up with anything for the top that's going to be the same. I could say x plus 7. It needs to be the same degree. I'm linear in the denominator, so I'm also going to be linear in the, actually that's not good math, because I do see a 0 here. I see a 0 here at x equals 1. There's a 0, right? So that tells me I need a term that is equal to 1, where x equals 1 is 0 in the numerator only. So this is actually the equation, x minus 1 over x minus 2. That's the exact equation. I'm quite sure. Oh, no, look. I'm zooming in a little bit more. No, that's not a hole there. Is that a hole? I don't think so. I think that... I don't know what they're going for with that. Can't tell what they're going for. All right. Now let's move over to this one. We clearly have a vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. So HA at y equals 0, a vertical asymptote at x equals 0. So we know the denominator has a 0 at x equals 0. So, or a vertical asymptote. So why don't we just say x on the bottom, right? Because if x equals 0, we're undefined. And we need the denominator to be higher degree than the numerator. So let me just put a 1 up there. Because 1 over x, that works. You can have 7 over x, 10 over x. These all seem possible. There's no zeros, right? This never touches this. All right, let's keep moving. Part 4, solve each rational inequality. All right, a rational function r is given as r of x equals x plus 10 times x minus 8, where all the intervals in which r of x is... What are all the intervals in which r of x is greater than 0? So we have to think about what's happening here. Well, we have a 0 at x equals negative 10, because that would only exist in the numerator. And we have a vertical asymptote at x equals 8. All right. So let's just make a little sketch of that. And maybe we don't have enough space here, but... So at negative 10 and 8, these are important spots. We have a 0 here at negative 10. And we have a vertical asymptote. It's late. A vertical asymptote here. So we want to know what's happening in this range. We want to know what's happening in this area, and we want to know what's happening in this area. So these 3 areas, which are, what are those 3 areas? Well, it's from, these little charts are popular. I've tried to avoid having you do them, but it's really the best way to do these. We want to know what's happening from negative infinity to negative 10, from negative 10 to positive 8, and 8 to positive infinity. All right, so now I can just pick a number between negative infinity and negative 10, literally any number. How about negative 20? And I substitute it in. Well, I get negative 20 plus 10 over negative 20 minus 8. And I get negative 10 over negative 28. Well, that's a negative divided by a negative, so that's a positive. So I'm positive over that interval. Now let's pick a number between negative 10 and 8. How about, I don't know, 2. So I get 2 plus 10 over 2 minus 8. That's 12 over negative 6. Well, that's a negative 2. That's a negative number. And now let's pick a number between 8 and infinity. How about 10? So I get 10 plus 10 over 10 minus 8. Get 20 over 2. That's a positive number, so it's a positive. So I'm positive, because it's asking when we're greater than 0, I'm positive over the interval. I'm going to use interval notation. Negative infinity to negative 10 and 8 to infinity. All right, let's try this one. I don't remember doing any questions like that in our notes. I don't know. All right, a rational function r is given as this. What are the intervals in which it is less than 0? Well, let's convert this to factored form in the top, and we're going to get x plus 10 times x. I'm tired, y'all. Hopefully I'm not making mistakes. Over x plus 10. Well, what do I notice here? I have a 0 at x equals 2. I have a hole here. Holes are not going to matter for this, right? Because it's just going to look something like, boom. It's not going to determine when we're greater or equal to 0. So really, I just need to know two intervals here. When we are but from negative infinity to 2 and 2 to infinity. Give me a number between negative infinity and 2. How about 0? So we get 0 squared plus 8 times 0 minus 20 all over 0 plus 10. That turns into negative 20 over 10, which is a negative number. So we're negative there. And what about from 2 to infinity? How about 10? So we get 10 squared plus 8 times 10 minus 20 all over 10 plus 10. Oh, we just really want to know if this is positive or negative. 100 plus 80 is 180, 160 over 20. That's, of course, 80, which is a positive number. And so we can say we are positive over the interval 2 to infinity. These ones will take some practice. Some of you, I think, will probably be unsatisfied with my answers. This is turning into an extremely long video. I need to go over a couple more questions. Let's just do this page together real quick. I think we'll have everything covered. All right, the rational function f is shown above and has a vertical asymptote at x equals 4, a hole at x equals 6, and a horizontal asymptote at y equals 5. Use the graph of f to answer the following questions. Which of the following limit statements about f is correct? All right, I'm going to read all of these. The limit as x approaches negative infinity, the f of x equals 4. So as x heads forever in this direction, well, we're not equal to 4. We're equal to 5. So this would be true if this was a 5, but it's not a 5. So that's not right. All right, the limit as x approaches infinity, the f of x equals 4. Again, as I head forever in this direction, there's a horizontal asymptote y equals 5. So that's my end behavior. This should be a 5 if this statement was true. It's not a 5. It's a 4. So this is not true. It's not B. Now we got to be able to read these. The limit as x approaches 4 from the left. The limit as x approaches 4 from the left. So as I come from the left side and I approach 4, f of x is headed towards positive infinity. Let's see. I'm going up towards positive infinity. That seems pretty good. C feels good. Let's check D. The limit as x approaches 4 from the right, the f of x equals positive infinity. Well, as I approach from the right side, where am I headed? I'm headed down. So this would be true if this was negative infinity. But it doesn't say negative infinity. So that's not right. All right. Which of the following limit statements about f is correct? The limit as x approaches 4 from the left, the f of x equals 6. I'll use a different color for this one. I'll use blue. As x approaches 4 from the left. So coming from the left to approach 4, it does not equal 6. We already went over this. Equals positive infinity. As I approach from the right, again, we already went over this. It's not true. It's headed towards negative infinity. The limit as x approaches 6 from the left equals 5. The limit as x approaches 6 from the left, where's 6? Oh. I'm approaching 6 from the left. It does not look like it equals 5. It looks like it equals 4. So that's not right. Oh, the limit as x approaches from the right equals 4. So as I get closer and closer to this hole, there is a hole there. So I can never get to x equals 6. But as I get to, 6.000000001, what number am I getting really, really close to? Well, I'm getting really, really close to 4. So this answer is correct. All right, which of the following limit statements about f is correct? As x approaches 5, the f of x is equal to negative infinity. As x approaches 5. You got to be able to read these correctly. They're trying to trick you. As I get close to 5, no, this is equal to 6. That's not right. As x approaches 5, we go to positive infinity. No, as we get close to, as x, yeah, that's just not right. All right, as x approaches negative infinity, the f of x equals 5. So as x goes towards negative infinity, does this go towards 5? Absolutely it does. Right here. As x, does it go to a 4? No, we have a horizontal asymptote at 5. So that means that's going to just be our end behavior. We're going to go towards 5. We're not going to go towards 4. All right, last question I'm doing with y'all. Which of the following could be the equation for the f of x? Well, all right, let's dive in here. What do we know about this? We have a horizontal asymptote at y equals 5. So our leading coefficients divided by each other needs to be 5 over 1. This is 5 over, right? Leading coefficient 5 over 1. That A's in play. B's in play for the horizontal asymptote. B and C are in play. D is not in play. This is 1/5. We'd have a horizontal asymptote at 1/5. So kind of each piece of information is my guess is going to let us eliminate an answer. All right, so what else do we know? There's a hole at x equals 6. So I need x minus 6 in the numerator and the denominator with an even multiplicity. Here that works, so A is in play. This, only x minus 6 in the denominator, that would be a vertical asymptote there. C is no longer in play. And here we have x minus 6 both. And what's the difference between these two? Oh, there's a negative sign here. Look, I did not see that. So this is really a negative 5. Look at that. It's hard to see. And it's 12:50. It's almost 1 a.m. So A is not in play. That's negative 5. So that just leaves us with our good friend B. This was a long video. I hope it was helpful. I hope you are studying. And good luck on your exam.